Okay, so Tao's analysis chapter 3. We're going to be splitting this into two parts. The first part is going to be about the Zermelo-Fraenkel axioms, and the second part is going to be finishing up the chapter. All right, so let's start with the set. So we're going to be defining sets axiomatically. Why? So let's consider the intuitive definition of a set, which is a collection of objects, right? But the problem with this definition is that we run into paradoxes, namely Russell's paradox. This is one of the problems. The bigger overarching problem is that that's very unrigorous. So Russell's paradox states that, let's say a set can be anything. So namely, I can say there exists a set such that X is the set of all sets that don't contain themselves. So you may be wondering, okay, what does that even mean? A set of all sets that doesn't contain itself. Let me write that out. So I'll let A be my set, and I'll say X is an A if and only if X does not contain itself. All right, so we haven't defined what a set is. We don't know that a set can't contain itself. Then we say, okay, does A contain itself? Because on the one hand, if we say A contains itself, that logically implies A doesn't contain itself. But on the other hand, if A doesn't contain itself, well, it's in the set, so A does contain itself. So we see we run into a paradox. This is blatant contradiction. So therefore, we have to define sets axiomatically. How are we going to do this? The Zermelo-Fraenkel axioms. Let's start with Zermelo-Fraenkel 1. Zermelo-Fraenkel 1 states that sets can be equal to each other. The conditions in which two sets are equal is if they have the same elements. This is 2. 2 is if they're equal to each other. So if I say that A equals B, this means that for every element X in A, then the element X is in B. Likewise, for every element X in B, then X is in A. You may be wondering, what if you only have one of these? Well, then you have a subset. We'll get to that later. All right. Namely, I can say like 1, 1, 2 is equal to the set 1, 2, because these contain the same elements. All right, now I'm going in a bit of reverse order. Let's go with 1. 1 is sets are objects. I like to put this one before the second one because it makes more sense. So sets are objects means that a set can contain itself, or a set can contain other sets. So namely, I can say I can have a set of 1 in it, right? And that's not equal to 1. Nor is this equal to 1. So these things are different. So sets are unique objects. One thing that will be very important is the empty set. So axiom 3 states the empty set exists. So what is the empty set? The empty set is such that X is in the empty set is always false. One thing that you can easily prove is that the empty set is unique. Assume that we have two empty sets, right, that are not equal to each other. Then we have, for every element X in A, empty set 1, X is in empty set 2. Why is this true? This is vacuously true, right? Vacuously true means that this is never true. So the whole statement is true. And likewise for the other implication. So therefore, these sets are actually equal to each other, and we have a contradiction. All right then. So there we have the empty set exists, and it is unique. That means that if there are two sets that claim to be the empty set, they were just the empty set in disguise. Now we can go on to our first lemma. So our first lemma is the lemma of finite choice. Next video, we're going to generalize this to, this is not finite choice, this is single choice. Next video, we're going to generalize this to finite choice. And the video after that, not the video after that, but like in chapter 8, we're going to generalize that to the axiom of choice. Okay, so single choice means that if X is a set and X is not equal to the empty set, then there exists some element A such that A is an X. Namely, we can choose this element, right? So that's the axiom of choice. Not the axiom of choice, that's the lemma of single choice. All right. Now, let's move on to 4. 4 states that for every object, there exists a set such that that set contains only that object. Basically, what that says is if we have an element, we can put a set around it. What 4 also, I'll write 4 part 2, 4.1, is that if we have 2 things, we can just add them to a pair set. This is called a pair set. This is called a singleton set. All right. Now we have pairwise union. So pairwise union is going to become redundant. This is redundant because you'll see the axiom of union plus the pairwise set generalizes this, but we'll still go over it for pedagogical purposes. So pairwise union states that for any 2 sets, A and B, we can create a union B. Namely, if X is in A union B, X is in A, or X is in B. Now, one thing that you can check about union is that it obeys substitution. That is, if A is equal to A prime, then A union B is equal to A prime union B. It's also associative. A union B union C is equal to A union B union C. Where did I put the parentheses? Actually, I don't know. Like, where is the parentheses? Is this right associative or left associative? Whatever. And we have commutativity. These statements are not hard to prove just by using the laws of logic. All right, then. Now we can move on to I guess I could do pairwise union gives us like generalizes the singleton axiom, like an n-fold iteration of the singleton axiom. But I'll move on to subsets. So subsets is just one part of the definition. So we note that A is a subset of B if for every x in A, x is in B. So it's 1/2 of the definition of equality. So namely, we can say that X is a strict subset. We denote X to be this is a strict subset if A is not equal to B, or a proper subset. I feel like that's the proper terminology. Yeah. So in general, we see this bar over. That means that it can include it. If we have like a crossed out bar, that means it's a strict or proper. All right. One thing about subsets that we want to know is that they form a partial order. What does this mean? It means that we have transitivity and anti-symmetry. These are the main things that we want to know. So transitivity is such that if A is a subset of B and B is a subset of C, then we have A is a subset of C. Anti-symmetry means that if A is a subset of B and B is a subset of A, then A equals B. All right. So why is this called a partial order? And that is because it's on a total order, right? So we have like some sort of ordering, right? Where we have clearly C is like the greater of A. But we can't compare any 2 sets. For example, I can't compare 1, 3 and 2, 5 because one is not a subset of the other. What would be an example of a total order is greater than or equal to on the real numbers because I can compare any 2 real numbers like that. All right, so that's going to be a subset. Let's move on to more axioms. Next is going to be the axiom of specification. Specification essentially states that if we have a property P of X, we can form the set X in A such that P of X is true. So basically, specification is exactly in the name. We're specifying, we take an existing set and we specify the elements which are true. One example would be intersections. So intersections, we can form, let's take any set A. We denote A intersect B to be all the elements in A, such that it's also in B, right? And we get this for free. We don't need an axiom or anything. We can also get set difference. So we can denote A set difference B, all the elements in A, such that the element is not in B. So that's specification. And in this case, our property for this one would be x and b. Property is that x is not in b. So it's true for this one if x is in b, and it's true for this one if x is not in b. Let's do a quick Venn diagram to see this. This is intersection. This is set difference. All right. Now let's move a little bit on to our next thing with sets, which is going to be that sets form a Boolean algebra. So Boolean algebra, there's a whole bunch of axioms that consider like a system to be a Boolean algebra. Two things that we want to know is partition and De Morgan's. So partition, this is not an axiom. This is something that we can prove. Partition states that A union X intersect A is equal to X, and A intersect X A is equal to the empty set. So typically in a Boolean algebra, we're considering X to be sort of our universal playground, and A and B to be sets within that universal playground. This is pretty simple, right? If we take A and the complement X, we can consider X union Y to be the complement of Y, right? Because if we already established that X is our universal playground that we're considering in, we can say, okay, if it's already established what playground we're working in, I'll just say the complement is the whole universe minus our little thing. So for example, let's say we've already established we're working in the real numbers, and I tell you the set 0, 1. Well, then our complement would be the set negative infinity to 0, union 1 to infinity. So complements will be useful once we get to De Morgan's. De Morgan's is a mathematical logic statement, but it can be translated into the language of sets. De Morgan's state that if we have this, well, we can find this by doing the terms like this. What do we put here? It's not a union, it's an intersection. Likewise, for the other case, what do we put here? It's a union. And we can rewrite this in the language of complements, tell us that A union B complement is equal to A complement intersect B complement, and A intersect B complement is equal to A complement union B complement. So think about complements are really like the negation in the form of logic, right? And unions is like or, and intersections like and. So if I tell you, hey, we don't have turkey or chicken, well, this means no turkey or chicken. So no turkey or chicken, that means we have no turkey and no chicken. Likewise, if I tell you we don't have turkey and chicken, this means one of them goofed. We either don't have turkey or we don't have chicken. All right, and we can consider that union and intersection are sort of like dual under this complement operation. Let's go on to 7, which is replacement. So replacement's exactly that. We're replacing elements of a set. Well, technically, most of the time we're working with exactly one, which would be replacement, but I guess you could do it most one. So replacement states that if you have P be a property, so P of xy is a property, so x is like an element of a set A, right? And we have this to be true for at most one y. P of x for at most one y. So I'll say for each x in A, there's at most one y. Such that this P of x is true, right? Then I can say that, what can I say? I can say that I can form the set y. Well, I can form the set like y such that p of x y is true. Namely, let's consider an example. Let p of x y be the property such that y is a successor of x. So I'll define this to be y is equal to x plus plus. And I'll let our set be 1, 2, 3, 4, 5. Then our replacement will exactly take our property and it will output our y's. So it'll output 1 becomes 2, 2 becomes 3, 3 becomes 4, 4 becomes 5, 5 becomes 6. So essentially, this allows us to create sets in the form we're applying a function to a set, right? So we have f of x such that x is an a. So we're replacing elements of the set x. Axiom 8, I'll just go over it. Axiom 8 is called the axiom of infinity. No idea why it's called this, but it essentially states that the natural numbers exist and the natural numbers follow the piano axioms. All right. Now, we noticed Russell's paradox, right? So in general, the axiom of universal specification is not true. Universal specification states essentially that we can form sets such that we can form basically any set with universal specification. But uh, Russell's set, Russell's paradox says, nope, this isn't true. So in order to further put a hole in this and say, okay, we don't want Russell's paradox, we get regularity, which essentially states that every set has to be regular. What does regular mean? I have no idea how they actually came up with this definition of regular, but apparently, in order to not run into these shenanigans, you have to say that if A is non-empty, so if A is not equal to the empty set, there exists at least one element of A. Well, that's finite choice, right? There exists, wrong symbol. There exists X such that X is an A. But we have one more thing. We have if X is a set, then X is disjoint from A. So it's the empty set. I have no idea how they came up with this, but apparently this is true for all the sets, and this helps us make sure that we don't have a set that doesn't contain itself. For example, if we have X containing itself, this axiom of regularity would not hold. But it holds for all ordinary sets, that's fine. All right, now let's move on to functions. So a function is a property, right? A property pxy, such that we have a domain x mapping onto a domain y. And we say that this property is true such that for every x, there's exactly one y. The exclamation mark before or after? I have no idea. Such that p of xy is true, right? So in other words, it's meaningful to write f of x is equal to y. All right, so it's not hard to verify that it obeys the axiom of substitution in the sense that if I have two different functions and they're equal, then their outputs are equal. We can consider the graph of a function, which is the set x f of x for all x and x. And one thing to note is that this is the domain and this is the range, right? In domain and codomain. In particular, the range is not equal to the codomain in general. The range would be what we note as the image of the domain. So it would be the what this graph part traces out. So for example, if I consider the function y equals x squared, the range is square numbers, while the codomain is real numbers. We'll see this more clearly once we get to images. All right. One clear thing about functions that we want to consider is function composition. What function composition is that if we have a function f, which leads a to b, and a function g, which leads b to c, we can consider the function composition fg, which leads a to c. In particular, f of g is equal to f of g of x. F of g evaluated at x is equal to f of g of x. it's not hard from here to see that function composition is associative. In fact, it's like one line. You just like plug stuff in and it falls out. So like often when we don't want to include associativity as an axiom, we'll just say we'll let them be noted as functions, right? Because associativity is applied as functions. Pretty nice thing. We also have injectivity and surjectivity. At first, these seem pretty unrelated, but once we see more examples, we'll see how they're actually kind of dual. So for example, injectivity f of x equals f of y means that x equals y. So what does this mean? We have one-to-one, right? So that means we can't hit anything in the codomain more than once. Surjectivity is we can't hit anything in the codomain less than once. We say that for every y, there exists some x, such that f of x equals y. This is how everything has a hit. No more than one hit. What if we combine these? That means everything has one and only one hit, and that's a bijection. So bijection is a one-to-one correspondence, different from a one-to-one function. And a bijection says that we have an inverse, right? We have an inverse if and only if we have a bijection. It's not hard to prove this. We can consider that an inverse, right? It swaps the pairs f. Like if we have a pair x f of x, like we have a pair f of x f inverse of f of x, which is just f of x. So an inverse means that if we have f composed with an inverse, we get back the identity. And if we have the f inverse composed with this, we get back the identity. It's important for it to be both a left inverse and a right inverse for it to be an inverse. All right. We denote a function to be its own inverse if and only if it is, or we'll say a function is an involution if it is its own inverse. So now let's go on to images. So images is, let's say we have a function of a set, right? So a function of a set, this is different from a function of a value. This is a function of a set. Completely different note. The notation is so confusing when we get to functions. Just try not to get confused. Think of it as a completely different thing. You can come up with your own notation, write it as something different, but this isn't a function of a value. Function of a set. We're looping over all elements of that set, and we're giving out what the function is. So for example, let's say my set is the doubling function. Then a function of the set 1, 2, 3, well, it gives me back 2, 4, 6. It tells me where the set in the image will, it tells me where the set in the domain will lie in the range. And yeah, it will lie in the range because the range is the image of the entire domain. So, namely, we can say a function is onto if f of the codomain is equal to the domain. In other words, the domain equals the range. We have inverse images as well. Okay, and we have inverse images. We denote f inverse of a set, I'll call it U this time, to be the set of all. Now we're considering the in the codomain, right? Such that, oh, not in the codomain. What am I telling? The domain. Oh, this should also be the domain. What am I doing? Oh, silly me. In the domain such that f of x equals u. So, in u. So it's essentially asking us, okay, I know what this function's output is. Where does it end up? So namely, I can say that f inverse of 4, 6, 9 of the set of the function f of x equals x squared is equal to 6 doesn't belong here. this just 2, 3. All right. Now we get to axiom 10, which is the axiom of power set. So the axiom of power set states that there exists a set a set of all sets from domain X and codomain Y. So if you have X into Y, there exists a set of all functions from X to Y. It's not hard to show this, but there are actually Y to the X of these functions, or at least the cardinalities of them. But do you know what mathematicians decided to name this set? They're just leaving it like this, Y to the X. That makes no sense. One specific example is if we have X to the true false, right? So this is essentially telling you, hey, for each element in the X, I'll tell you if it's in or not in my new thing. So this is essentially just telling you function, right? A subset, right? Each element is either in or not in. So there's 2 to the X of these. But do you know what mathematicians decided to call the set of all subsets? Exactly. It's literally denoted as 2 to the X. It's not a number. It's literally denoted as 2 to the X. Makes literally no sense. Next is the axiom of union. Axiom of union states that if you have a set of sets, we can contain a union of them. So what does this mean? Let's say let's A be our set of sets, right? A is our set of sets. Now I can say that union A, if, let's see, I'll say that if X is in union A, then X, how would I formulate this? This is a good question. I'll say that if X is in, let like B1 through Bn be like the set of sets. And I'll say X is in B1 Bi for like I in this range, right? Yeah, so axiom of union generalizes axiom of pairwise union, in fact makes it redundant. Because if I take two sets A, B, I can use pair set to form A, B. I can use union to form union A, B, which is our definition of A union B. And A and B are sets. All right, intersections we don't need an axiom for because that can be found using our other axioms. And that is Zermelo-Fraenkel. Tune in for the next video.